Very good. Welcome back. After a minor glitch at the end of the first half of this lecture, now we're ready to proceed. We had uh, gotten to the point where we could derive Bayes' rule from the method of maximum entropy. And so what I was saying as my class got interrupted was that the great advantage of having a maximum entropy derivation of Bayes' rule is that now we can generalize it in various ways. Okay, so where did Bayes' rule come from? We had information in the form of a prior distribution, information in the form of data, and information in the form of the relation between the x's and the thetas, and that was given by the likelihood function. So whether you just use the principle of minimal updating directly, or you use the principle of minimal updating as implemented by the ME method, you still get the same rule. The posterior is going to be given by Bayes' theorem. So how do you generalize this? Well, there are many ways. For example, here we have a prior. Yeah, you always need a prior, so we can't change that. But suppose that instead of having the information in the form of data x prime, a value for what the data is, you have this form of information supplied in other ways. Or what if the information about the likelihood is supplied, the relation between x and theta is supplied in other ways. So you can appreciate that under those circumstances, you're going to get something that smells like a Bayes rule, but with differences. So I'm not going to go over all of these. I'm just going to cite a few examples. I'll let you do a couple of them for homework. One generalization is when instead of knowing the data precisely, you have uncertain data. This is what leads to what is called Jeffrey's rule. And the way that one works is we impose as a constraint on the posterior the fact that this here is not a delta function, which is what we had in the derivation of Bayes' rule, but rather some other function. Let's call it just p d of x, some probability distribution which may be centered about x prime or not, it doesn't matter. So when you use this as the constraint, you get a probability distribution, a modification of Bayes' rule that goes like this. We just integrate the posterior that we got. You see the part of the probability distribution px theta is just px. That is just a function of x, is exactly what the constraint was, and the part that is the remaining piece that's given by the product rule is unupdated from the prior, and when you do that, you get something like q theta integral dx p dx, and then here we have the usual part of Bayes' theorem. So when you have uncertain data, you just replace the delta function for the value of the data with another probability distribution, and you're done. So that's one way to generalize it. It's a way of generalizing this B part of the information that goes into Bayes' theorem. But suppose that instead of having a probability distribution for what the x's are, suppose that you have some other form of information too. One possibility is that you have moments of x. So the data information, we have information about moments of x. Instead of having the value of x or the probability of x, we have moments. So you see it's even less information. It could be any function, the expected value of any function of x with some function like that. This is some value. Well, use this in the method of maximum entropy and you get an expression. This leads to something, and eventually you have your posterior is given by a prior, and then there is some funny sort of integral that involves the Lagrange multiplier associated to that constraint with some normalization factor, and then here we have the likelihood function. So once again, you can see that the structure of this formula is very much like Bayes' theorem. You have a prior, you have information, or rather a probability distribution about what this variable x is, and then you have a relation between x and theta. So that's another possible generalization. 3, here is another in which you have information about moments. So you have data and you have moments of theta as well. So in this particular case, you have not only the prior, and you have data, and you have a likelihood function, but also you may have moments of theta, where here we have, for this constraint here, you may have something like this. F theta equals F. As you can appreciate, once we have the prior on x and theta, this is going to give you one delta function, and this is going to give you something else that you require additional Lagrange multipliers. The net result for that one is something like p theta is equal to q theta. Then you have Bayes' theorem, just as if you didn't have this Lagrange multiplier. And then you have yet another lambda f theta with a partition function. So this is an interesting hybrid, isn't it? Look at this. This part is Bayes' theorem. When you don't have that constraint, the f constraint, you set lambda equal to 0, then you don't have that constraint, you just recover Bayes' rule. On the other hand, if you don't have likelihoods or anything of this sort, what you have here is maximum entropy, where you're just maximizing with a constraint, and you get the standard Boltzmann distribution. So it's kind of cute. Anyway, the whole purpose of these exercises is to see that exactly the same machinery, if you put more information, it can be processed and you get conclusions. Let me give you one more just to point out what's we're going here. Suppose that, and this is the last one I'm going to give you, suppose that you have an unknown likelihood. Now, in all of this, the likelihood has been essential because you're essentially going to make inferences about theta on the basis of x's. You need a relation between x and theta. But what if you don't know that? This is what is called the Zellner method of moments. In fact, what I'll present very quickly here is just a generalization of the method of moments. The idea here is that we have the prior x theta is going to be q theta, and then instead of having the likelihood function like we normally have, you say, no, we do not know that. As far as we are concerned, as far as our prior goes, there is no relation between x and theta. Under these circumstances, then the connection between x and theta has to be given by the constraint. So the constraint is what supplies you with the relation between x and theta. And that could be in the form of, I don't know, some expected value, for example, px theta of some function x theta, and this gives you some expected values of x. So here you have functions of x and theta, and you're given information of this form. How you would know these things? You can simplify this by having just powers. That's why it's called the Zellner method of moments. And then, of course, you have data. So this is obviously another way in which these things can be generalized. And so under these conditions, the posterior for theta is going to be the prior for theta multiplied by a bunch of Lagrange multipliers that may depend on the data and so on, divided by a normalization that in this case may depend on the data as well. The particular end result, the formulas that arise from these various generalizations of Bayes are not particularly important unless, of course, you're concerned with the practical problem of putting these formulas to good use. The point I would like to make here is more along the lines of this is how you would reason if that is the piece of information you have. You can see that you can do an incredible amount of damage by including information in the form of various kinds of constraints. Incidentally, when we get back to the problem of doing something actually useful with this kind of maximum entropy method, something like deriving quantum mechanics, the crucial difficulty in deriving a theory like quantum mechanics from this kind of formalism is going to be precisely what are you talking about? What are your x's and thetas? That tells you what is the entropy that you want to maximize. What's your priors? That part is easy. What is the priors? We're just going to put them flat. But then what are the constraints that you're going to put into the formalism? This is where you put the physically relevant information, and choosing those constraints is the crucial difficult element. But we're talking about constraints. So now let me make comments about constraints. So to finish this class, I want to talk about constraints. The issue is what happens when you have different constraints. Suppose you have several constraints. Do you apply them one by one, or do you apply them sequentially, or do you apply them all together? Which one is it? So does it matter what order you apply your constraint versus non commuting constraints. Which one is it? How do you choose this? If you do this wrong, you're going to get your answers wrong. So this is important. The point I'm going to be making here is that whether you put your constraints in one order or in another will matter, and that is part, or how do you make the decision about which one you do, is actually part of deciding what is the piece of information that you want to include in your problem. So it's problem specific. You have to actually understand what it is that you're doing. So let me go over this. We had one example of commuting constraints where we actually knew pretty well what we were doing. This is the case of data information, data constraints when you're doing Bayes rule. In Bayesian updating, so here we start with an example. Here we do Bayesian updating. The idea here is, suppose that you have an experiment that can be done many times. And the data comes in the form of x1, x2, x3, and so on. And so the likelihood we're assuming that each one of these experiments is independent from each other. And so the likelihood function is going to be something like this. You do n of these experiments, and the likelihood function is going to be something like that. And I'm going to make the assumption here that these experiments are independent. So you're going to have qx1 given theta multiplied by qx2 given theta, and so on. So this is where I tell you that x1 is independent of x2. Now, one thing that I would like to emphasize here, there is a typical sort of mistake that sometimes is made, in which you say, okay, you measure x in experiment number 1. You measure x in experiment number 2. You measure x in experiment number 3. There is something that's misguided or misleading in that sort of expression, because it gives you the impression that you're measuring the same variable once, and then the same variable again, and then the same variable all over again. And that's not quite true. You're measuring variable x1, and you're getting x1 prime. You're measuring variable x2, and you're getting value x2 prime. You see, when you say, I'm measuring the length of this table, my first measurement is x1. Then I'm going to say, I'm going to measure the length of this table. My second measurement is x2. Does the x1 contradict x2 if they're not the same? No. The value x1 is the length of the table in experiment 1. The value x2 is the length of the table in experiment x2. They need not be the same. Okay, there may be fluctuations. Maybe the table is doing something wacky, right? That's exactly the point I'm making. So no, you're not measuring the same variable in all of these experiments. You're measuring different variables. That's what accounts for there being several of these factors here. In particular, it means that once you have the measurement x1, when you measure x2, that does not contradict the fact that in the first measurement, the result was x1 prime. Once you made the measurement of x1, you cannot unmeasure it. So in this case, so x1, let me put it like this, x2, and so on, are different variables. You may call it the length of the table, but it is the length of the table at time t1, the length of the table at time t2, right? And so when you actually do Bayes, and you're trying to predict or infer the value of theta on the basis of measurements of x1, x2, x3. So what you have here is x1 theta prime, qx1 prime, qx2 theta qx1 2 prime, and so on, right? So you can see clearly here that if you have them in one order or if you have them in the opposite order, it doesn't make any difference. The order does not matter. The order does not matter. In this case, in this particular case, you could first update with x1 and then with x2, or you could update with x2, then with x1, they commute, or you could update with x1 and x2 and they still get the same answer. And the reason, this is the crucial point, the reason these constraints commute is that when you apply the second constraint, the second one is not affected. Let me put it clearly. The information supplied by the first constraint does not become obsolete when you apply the second constraint, the independent constraints. So the information supplied by x1 prime is independent of that supplied by x2 prime. One does not make the information of the other obsolete. Very good. Under those circumstances, things commute. So now, when is it that things would not commute? Now, that's non-commuting constraints. Let's consider two situations. A, you have a prior, Q. I supply you with information in constraint C1. This produces a posterior P1. And now I'm going to give you another constraint. You maximize yet again. And this provides you with another posterior, it leads you to another posterior, which I'm going to call PA because it's case A. Now, what is the situation here? Let me draw a little picture for you. The idea here is I have let me go to the next page. In the space of all probability distributions, I have a prior Q. The space is the space of the page. That's the prior. And now I give you a constraint C1. And when I try to maximize, I maximize the entropy of P's here relative to Q, which is the one that is selected. It's the one, remember how this works? I'm going to rank according to entropy, and then the one that is barely tangential there, that's the one that has maximum entropy for all the probabilities within this constraint. Any other probability that's further in has lower entropy. So The selected posterior is this one here. Let me call it P1. Now I'm going to apply another constraint. Let me draw it like this. This is constraint C2. And so now the question is, if this is my new prior now, and I want to figure out the best probability distribution here, the one that's going to be selected is going to be there. So I went from Q that way to that way, and this is the PA that I was describing down here. Now notice what happened when I've done this, and I've drawn my bubbles. I've drawn my constraints in such a way as to make this point more or less explicit. When I maximize entropy to update from Q with information C1, I maximize and I choose any probability within this bubble, within this constraint. I choose the one that maximizes entropy. Now, implicit in those words that I have just used is that when I maximize subject to this constraint, I'm going to pick a probability distribution within this bubble. All probability distributions outside, those that do not satisfy the constraint are completely ruled out. So when I say I start from Q, I apply the constraint C1 and I land here. And now I tell you, oh, look, this is the important part. Now I tell you, now I have a new constraint C2. If I maximize from this prior into C2, I have to ask the question, am I going to pick a probability distribution that lands within this constraint? And I am assuming that everything that lies outside that constraint is completely ruled out. If that is the case, what I'm saying is, this is the constraint, these are the allowed probability distributions. Anything outside is ruled out, including the old probability distributions that will land in here. And so I'm going to say C1 is obsolete, C2 is the one that replaces everything. I'm going to go from this prior to a probability distribution that satisfies C2, and that gives you PA. That's the posterior. That's the situation that I'm describing when I write something like this here. When I impose this constraint, this implies that C1 is obsolete. It's going to be completely replaced by C2. On the other hand, we could have a situation where we say we have the prior Q and we are applying a constraint that is C1 and C2. In this situation, we fully recognize that, yes, we do have a new constraint, but the old C1 is still applicable. It still remains correct. Under those circumstances, we evolve to CB, and if I were to draw it all over again, I would draw something like this, where I start from Q, and then the update is directly to the intersection of C1 and C2, and that is PB. So you can clearly appreciate that PA and PB are different. Not only they're different, they're both correct. The fact that you have two different probability distributions is just a manifestation of the fact that you're dealing with different kinds of information. In the case B, both C1 and C2 are correct constraints. In the case A, C1 was correct at first, but then it got revised. You say, no, this is no longer operative when I update now. External circumstances have changed. C1 is no longer true, so that's the different constraint. There is yet a third case in which you update from Q with C1 to P1, and then you say you acquire information in the form of C2, but C1 remains operative. Under those circumstances, the updates would go like this. You go from Q to P1, so this is C1 and this is C2. And then from P1, you have to update to this region here. And so it's an interesting question to ask, what under those circumstances is going to be the actual result? It turns out to be the case that the result is PB as well. So the result is something that takes you to PB. It's actually very pleasing. You can go from Q to PB directly, or you can go from Q to P1 to PB, but you have to be very careful. Notice, when I do this, I'm saying, look, yes, C2 is new information. It changes the probability distribution that you pick from within C1. C2 is new information, but C1 is not obsolete, so you have to keep imposing it. So when you apply different constraints, you have to be very careful about what order you do it. They mean different physics, okay? What else? I think we're done with this. We can draw our conclusions here and summarize. The summary here is what I started with earlier. You have a method of maximum entropy that is constructed by ranking probability distributions. You update according to a ranking probability distributions in a way that you value prior information. You value independence. You're trying very hard that when you incorporate information into your problem, the information is incorporated explicitly. You do not want the updating tool, entropy, to introduce unwarranted correlations into your problem. Since the whole of physics is about correlations between this and that, you can probably appreciate that this is like really important. Let me see. What else can we say here? The method ME can handle arbitrary priors, which maxent couldn't, and it can handle arbitrary constraints. In other words, arbitrary forms of information, which Bayes couldn't. So ME unifies maxent and Bayes. Very good. I believe that this is basically, well, it sort of provides a certain sense of completion to this method of maximum entropy. There is one extra topic that we want to discuss concerning the method of maximum entropy, and this is going to take us a few lectures, and it is the following. When you have a prior, you are in the space of all probability distributions you have a prior and you get a constraint. Here's the constraint. And you want to pick the best probability distribution within this constraint. What you do is you rank. And so here you have decreasing entropy. And you rank all probability distributions, and the ones that land right on the tangent here are the ones that are maximum entropy. This is larger entropy than those inside. So now the question that we could ask immediately is the following. What if you have a probability distribution that's right there, very close? The entropy is very, very close. So if you have your entropy maximum, yes, you should prefer the one that is at the very top. But the ones that are close to it have almost the same entropy. Do you totally rule them out? Or is there a way of getting even better inferences by saying, look, yeah, this probability distribution will contribute the most. This is the one you should pick. But the ones that are neighboring to it are pretty close too. So maybe we can even improve further our updating by incorporating some of their effects as well. You can probably appreciate that what I'm doing when I say this is that, yeah, pick the maximum of entropy, but probability distributions that are very close to the maximum may actually be relevant. This will include effects of fluctuations. That's what we're going to be doing next, extending the reach of the method of maximum entropy to incorporate situations where the entropy maximum is not very sharp. In order to do that, we're going to actually try to have figure out when you have two probability distributions that are close together. What do you mean by close? Is there a unique measure of the distance between probability distributions? Can we distinguish two probability distributions that are close together? And this is going to, that kind of question, how do you talk about whether probability distributions are distinguishable, distinguishability, and this is what's going to lead us to the subject of information geometry. That's for the next class. See you then.